All right, let's get started. Good morning, everybody. Welcome to Chem 1105 and your host, me, Dr. White. I hope you're all excited for another wonderful morning of chemistry. Don't you love chemistry? I do. All right, important things. This Thursday, I will be giving at the After the Lab test number 2. You should have all seen, but let me show you. Thumbs up, people. Do you see on Thursday on your screen? Thank you. All right. On Thursday, I'll be giving test number 2 online, just like test number 1. You'll download a PDF file for test number 2 from the assignment area. It will be available Wednesday. Thursday, right after lab, around 10 o'clock, I'll send out an email for the password for the 2 versions of test number 2. You'll get one of them. You have until 11:30 to finish test number 2. Upload your answers as a single PDF file, and it should take you about 40 minutes. If you need a couple extra minutes, don't worry, as long as you get it in by 11:30. All right, test number 2 will cover chapter 4 and chapter 5, part 1. This covers chemical bonding, including ionic and covalent chemical bonds, and it will cover mole and mole-related things, including balancing chemical equations. Test has 18 problems, 9 pages, no multiple choices test, but some of the questions are multiple part, like part A, B, C, and D. Chemical bonds and related topics like ionic and stuff like that, covalent, 50 points. Moles and mole-related topic, 55. If you notice, it adds up to 105. Why? Because there are five bonus points. Now, the way I do bonus points on a test, I don't have a certain problem that's the bonus problem. No, I just have the whole test to add up to 105. So there's 5 bonus points. And tomorrow I'll do my world famous review for the next test number 2, in our Zoom meeting. On Thursday, we'll have our regular Zoom meeting for our lab, and afterward, you'll take test number 2. Be sure, I'd highly recommend that you go to the lecture section of Blackboard and look at important information, test number 2. Those are things you should know how to use, but you don't have to memorize. Boy, it's Thursday, Monday morning. I've been up for a while too. That's probably it. But anyways, make sure you check that. In the past, I would have students memorize things. Now I've cut that way down. There still is some memorization. The best way to study for test number 2, do the practice problems. Today, I'll be doing part 5 or chapter 5, part 1, the 2 different types of mole problems. I decided to split it up because I can do that. But anyways, tomorrow I will go through the problem set on balanced chemical equations. On test number 2, there will be 4. Oops, it's broken. 4 balanced chemical equations that you have to do. On any test or final I give, if I ask you to balance chemical equation, unlike the lab, you're going to have to balance it. The answer is already balanced will never be correct on any one of my tests or final. Remember that. All right. Any questions on test number 2? By the way, Friday, I don't wear them now because I have amplified speakers. I got my new hearing aids. I gotta go back and get them adjusted again, but they're pretty good. That's standard SOP with, if you don't know what SOP is, standard operating practice. That comes from industry. That's SOP for hearing aids. You got to go back a couple times to get them adjusted, but they're pretty good. And they were a lot less money than if I went to Costco than if I'd gone to a audiologist, like a couple $1,000s less. And Costco's quite good, at least the one I went to. And I've heard others people like them too. All right, no questions on test two. All right, personal announcement. First of all, today, at 5 and the rest of the semester, I'll have my office hour. However, Wednesday, something came up and I'm going to have to start my office hour at, I think, 8 p.m. And I'll be there for an hour. If you need me longer, I'll send out an email. But this Wednesday, my office hour will be 8 p.m. All right, let's get to work. Now, and I should open it up. Let me open something else up. All right, thumbs up, people. You see important information on your screen. Thank you. All right, these are things you should know. And the first thing I want to cover is 1 mole of an element equals Avogadro's number. And you should know 6.02 times 10 to the 23rd is Avogadro's number. But 1 mole of an element equals Avogadro's number of atoms of that element. And 1 mole of a compound equals Avogadro's number of molecules in that compound. Now, to remind you how to use your good buddy, your good friend unit analysis, whenever you have A equal B, like I just said, 1 mole of a compound equals Avogadro's number in molecules, there are always 2 ratios you can have, A over B and not equal, but and B over A. These are 2 separate ratios. So whenever you have something equals something else, you can have 2 ratios, one side over the other and the other side over the first side. And that you should remember. All right, everybody, can you see chapter 5, part 1, mole problem part 1? Thank you. All right, let's look at a question. How many molecules are 6.22 moles of hydrochloric acid, HCl? What are you being asked to find? Molecules of HCl. What are you given? How many moles of HCl you have? Now, the moles is all we have to start with. What units do we want to get our answer in? Molecules of HCl. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. Why? Because remember, anything divided by itself equals the number 1, meaning it cancels out. So if I have moles divided by moles, it's gone. So if I have molecules of HCl on top and moles underneath, where do I get these numbers to go in there? 1 mole of a compound equals Avogadro's number of molecules of that compound. So on top, I put Avogadro's number molecules of HCl. Underneath, I have moles of HCl. And Jada, yes, this is going to be on test number 2 this Thursday. Can you guys keep a secret? If I'm going over problem sets for stuff I'm going to tell you is going to be for that test, that means everything in the problem set is fair game for me to ask questions on. Because on all my tests, every question, I'll cover the concept behind that question at least twice, usually more, in lecture here. Nothing from the lab ever goes into the test unless I talk about it in the actual lecture part. Okay? So this is all going to be stuff you should know for test 2. And same thing tomorrow, balanced chemical equations. So next on test 2, it will say underneath your name, like test 1, please use proper significant figures for all calculated answers. And if you notice here, I have 3 significant figures, 6.22, 6.02 times 10 to the 23rd. Ignore this for significant. 6.02, 3 significant figures. 1 is an exact number because it's by definition 1 mole. Or Avogadro's number is actually calculated from experimental data. And therefore, when you do multiplication division, your answer should have the same number of significant figures as the number you're multiplying or dividing that has the fewest, except you ignore exact numbers. And therefore, here's my answer, 3.74, 3 significant figures times 10 to the 24th. Now, let's look at number 4. And 2 and 3 are similar, except we're elements, but I like molecules better. That's just my preference today. How many moles are 8.222 times 10 to the 17th molecules of oxygen gas? Oxygen gas, O2. So we're trying to find moles of O2. We're given molecules of O2. The only thing we have to start with is this number. What units am I trying to get to? Moles of O2. So this goes on top of my ratio that I'm going to multiply this number by. Underneath, what I'm trying to get rid of, the molecules of O2, I don't want that in my answer, goes underneath. And where do we get this number? 1 mole of a compound equals Avogadro's number of molecules of that compound. So this molecules of O2 divided by molecules of O2 cancel out. We're left with moles of O2. Where do we get the number? 1 mole equals Avogadro's number. 4 significant exact number. Number 1 is exact number 3. And do the math, and our answer is, yay, it's 3 significant figures. One of these days, maybe tomorrow, if I remember, I'll bring in my slide rule. I don't think I did a show and tell on that yet. If I did, somebody let me know. Now, let's look at important information again. Next 2 things you should know. 1 mole of an element equals the atomic weight of that element in grams. 1 mole of an element equals the atomic weight of that element in grams. And 1 mole of a compound equals the molecular weight of that compound in grams. 1 mole of a compound equals the molecular weight of that compound in grams. So the molecular weight is the sum of all atomic weights of that compound. The molecular weight is the sum of all atomic weights in that compound. So if we go back to our problem set, what's the molecular weight of sodium bicarbonate, baking powder? Well, there's 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygen. Now, on test 2, underneath your name, it will say, please use proper significant figures for all calculated answers. And it will say now, please use 3 significant figures for all atomic masses. That's going to make your life a lot easier. If you don't, I'm going to take off a point, so make sure you follow directions. And actually, it'll make your life easier. Now, if we look at the periodic table for oxygen, what's the atomic weight? 15.999. I'm going to let you round that off to 3 significant figures, then I'll do it. Go. All right, time's up. Keep the 1, keep the 5, keep the 9. Those are your 3. Use the next 9 to round off. Is that 4 or higher, or 5 or, 4 or less, 5 or higher? It's 5 or higher. So those 2 9s I drop. The 1 in front after the 8, I increase by 1. Well, that gives me 1.0, and add that to 15, and I get 16.0. Now, if we look over at sodium, Na, same thing will happen. When you round that off to 3 significant figures, that's 23.0. Let's do one more while we're in the neighborhood. Hydrogen. Underneath, the atomic weight is 1.008. Round that off to 3 significant figures. Go. Time's up. Keep the 1, keep the 0, keep the 0. That's my 3 significant figures. Use 8 to round off, 4 or less, or 5 or higher, and 5 or higher. Drop that, increase the 1 in front by 1. So to 3 significant figures, the atomic weight of hydrogen is 1.01. Now, here we have 1 sodium, 1 times 23.0, 1 hydrogen, 1 times 1.01, 1 carbon is 12.0. And hold on one sec. Let me do 6, and I've already done 2 of those. Why don't you come to my office hour for that if you can, or see me tomorrow before class, because I've got to get through certain stuff right now, okay? All right, and I'll try if I finish this early, remind me, and I'll try and do that again today. All right, now for the molecular weight, we have 1 sodium, 1 times 23.0, 23.0. This 1, 1, 1, and 3 are exact numbers. For hydrogen, it's this. Carbon's this. 3 times 16.0 is this. Now, when you add them up, you get 84.01. When you do addition, you get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest significant figures to the right of the decimal. In this case, first one is 1, second one is 2, next one is 1, 48.0 is 1. So you have to round off 84.01 to 1 significant figure past the decimal to the right of the decimal. Keep the 0, use the 1 to round off. That's 4 or less, drop it. And the correct answer is 84.0. And I give another one here, number 5. All right, now that you know how to do molecular weight, let's look at number 7. Number 7 is how many moles are 45.33 grams of sodium chloride? Don't forget to pass the NaCl. Chemists say that when they're at a restaurant. I do when I'm with other chemists. All right, so now what are you being asked to find? Moles of sodium chloride. What are you given? 45.33 grams of sodium chloride. And now if we look at this, the question is, how do we do this? Well, you use your good buddy, your good friend, unit analysis. Whatever we're starting with, we put there, and this is the only number we have. What units do I want my answer? Moles of sodium chloride. If I have a ratio, I can multiply this number by what goes on top, whatever we're trying to get to, moles of sodium chloride, what goes underneath, whatever we're trying to get rid of. We don't want grams sodium chloride in our final answer. And now where do I get the ratio 1 mole of sodium chloride, a molecule or compound, per grams of sodium chloride? Wrong thing. Right thing. And 1 mole of a compound equals its molecular weight in grams of that compound. So first I have to calculate the molecular weight of sodium chloride, which is the sum of all atomic weights. And I can do that. If you notice right here, MW is shorthand for me. I use molecular weight sodium chloride, 1 sodium, 1 chlorine, atomic weight of sodium, the 3 significant figures, 23.0. For chlorine to 3, 35.5, and it adds up to 58.5. So that's the molecular weight of sodium chloride. 1 mole of sodium chloride equals the molecular weight, which is 58.5. And now grams of sodium chloride divided by grams equal 1. I'm left with moles, 4 significant figures, 3 exact number. Here's my answer to 3 significant figures. Now, if we look at number 9, did any of you ever watch the Woodstock movie? When they did soundtracks, they were going number 9, number 9. Anyways, back to chemistry. How many grams are 5.21 moles of water? I'm going to assume for test 2, 3, 4, and the final, you all know water is H2O. Remember, water, that stuff is H2O. So, number 9, I'm trying to find how many grams of water, H2O. I'm given how many moles of water, H2O. So I have this number I want to start with. That's all I have. I want to go to grams of water, H2O. The O sort of got cut off. Anyways, whatever I'm trying to get to, when you use your good buddy, your good friend, unit analysis, grams of water goes on top, moles of water I want to get rid of goes underneath. Where do I get these two numbers? 1 mole of compound equals the molecular weight of the compound. What's the molecular weight of water? Over here, 2 hydrogen, 1 oxygen. The atomic weight of hydrogen is 1.01. The atomic weight of oxygen to 3 significant figures, 16.0. 2 times 1.01, 202. 1 times 16.0, 16.0, get 18.02. But 16.01 past the decimal to the right, significant figure, 0.02, 02, 2 to the right is significant figure, which is smaller, 1. Round this off to 1 to the right of the decimal point. Keep the 0, use the 2 to round off. Is that 4 or less? Yep, and I drop it, and the correct answer for the molecular weight of water is 18.0. And therefore, I can put 1 mole of water, 18.0. And now, if we go back, moles of water divided by moles of water cancel out. I'm left just with grams of water. Do the math, 3 significant, 3. I answered 3 significant figure. Now, for that one, I have it in decimal form. For those of you who had it in scientific form, that'd be 9.38 times 10 to the 1, which is correct. Both are. All right, now, special request time. Somebody asked me, could I do one more from 1 through 5? Let's do number 3. How many moles are 5.45 times 10 to the 22 atoms of silver? We're trying to find moles of silver. We're given how many atoms. This is the only number I have to start with. I do. I can multiply it by a ratio. What units do I want my answer in? Moles of silver. Moles of silver would go on top. That's what I'm trying to get to. Atoms of silver go underneath. And 1 mole of silver equals what? Avogadro's number, 6.02 times 10 to the 23rd. Atoms of silver cancel, divided by atoms of silver cancel out. And you're left with moles of Ag. Yay, we're on the right track. And do the math, and you notice 3 significant figure, 1 mole. The 1 is the exact number. So my answer is 3 significant figures. Hopefully all of you know how, hold on, let me find mine. Know how to use your calculator and scientific notation. If not, come to my office hour or come to class early. I usually log on about 10 minutes early, get my tea and then come back. But if you come in a little early and I'm already on, ask a question. If we do one more, number 12, how many moles sodium hydroxide, NaOH, excuse me, are 44.5 grams of NaOH? We're trying to find moles of NaOH. We're given grams of NaOH. Start with grams. What units am I trying to get to? Moles of NaOH. Use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever units I'm trying to get to go underneath. Where do I get a ratio? 1 mole of a compound to its weight of the compound. I look at 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights of that compound. And that will be given to you. So here's what I have to start with, trying to get the moles of NaOH. And this goes on top of the ratio moles of NaOH, trying to get rid of grams of NaOH. This goes underneath. 1 mole of a compound equals how many grams? Its molecular weight. And over here, the molecular weight of sodium hydroxide, 1 sodium, 1 oxygen, 1 hydrogen, add it up, get the right number of significant figures to the right of the decimal, which is 0, put them in, grams NaOH divided by grams NaOH, calculate, cancel out, 3 significant figures, 3 significant exact number, 3 significant figures. All right, any questions on that problem set? All right, let's move on to the next one. And if you haven't done these, I highly, highly recommend that you do this. Now, when we look at a balanced chemical equation tomorrow, I'll go through balancing chemical equations. It's important to know the coefficient in front means something. Everybody see my whiteboard? I guess it is because it's for Dr. White. Oh, is that lame? You should have a discount because you gotta have to put up with my bad jokes and humor sometimes. Sometimes it's pretty good. All right, everybody see the balanced chemical equation with hydrogen, oxygen, water on your screen? Thumbs up, people. Anybody out there? Hello? Thank you. All right, now, this is important to know. The coefficients, the number in front, tell you molar ratios. And what this means is 2 moles of hydrogen reacting when there's no number, and a lot of you missed this on the lab, 1 mole of oxygen to make 2 moles of water. Remember the coefficient, the number in front, gives you molar ratios. So for every 1 mole of oxygen, I make 2 moles of water. For every 2 moles of hydrogen reacting with 1 mole of oxygen, I make 2 moles of water. And that's important. The coefficients give you molar ratios. So let's look at the following. Number 1, thumbs up, people. You see mole practice problems part 2 on your screen. Thank you. All right. Now, I have C2H6O, ethanol, oxygen burns to give CO2, 2 moles of that, and 3 moles of water. So given this balanced chemical equation, if you react 5 moles of C2H6O with an excess of oxygen, when you see excess of something, that means ignore it because you've got enough oxygen in the world that will react with anything oxygen will react with. Then how many moles of water are produced? We're trying to find moles of water. We're given moles of C2H6O, ethanol, those stuff they put in gasoline, and don't drink it for the gasoline, but they also put it in things like vodka, Canadian Club, and other good things they're found in ethanol. But anyways, back to this, you're given this chemical equation also. So we have 5 moles of ethanol. We're trying to get 2 moles of water. How do we proceed? If I had a ratio, moles of water goes on top, moles of ethanol, C2H6O, goes underneath. Where do I get these numbers? Notice up here, 1 mole of C2H6O reacts with oxygen to make 3 moles of water. So for every 1 mole of C2H6O, I make 3 moles of water. And that's where I get 1 mole of C2H6. Doesn't look like a 6, but it is. O makes 3 moles of water. These numbers, coefficients, are exact numbers. So this is 3 significant figure, exact number. My answer should have 3 significant figure, and that's what we get. And if we look at the next one, same thing. You have a balanced chemical equation. If you react 7.50 moles of NO2 with excess water, H2O, how many moles of nitric acid, HNO3, are produced? So we're trying to find moles of HNO3, which is why I have a question mark there. And you're given 7.50 moles of NO2. This is the only thing we have to start with. What units am I trying to get to? Well, we figured that out. Moles of HNO3. Now, using your good buddy, your good friend, unit analysis, whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get those numbers? From the balanced chemical equation. Where do I get a relationship between moles of NO2 and moles of HNO3? For every 3 moles of NO2, the coefficients tell you moles, I make 2 moles of HNO3. For every 2 moles of NO2, I make 3 moles of NO2, sorry, I make 2 moles of HNO3. And these are exact numbers. For every 3 moles of NO2, I make 2 moles of HNO3. Moles of NO2 divided by moles of NO2 cancel out. I'm left with, yay, the answer I want, unit-wise, moles NO3. Notice 7.50 is 3 significant figures. 2 and 3 are exact numbers, and my answer is 3 significant figures. And that's how you do that. Now, let's look at number 4. And number 4 has this balanced chemical equation. C3H8 is propane. That's the gas you buy in those white tanks for your barbecue. Propane, C3H8. If you react 1 mole of propane with 5 moles of oxygen, you get 3 moles of CO2 and 4 moles of water, plus a lot of heat, which we don't put down in the balancing of a chemical equation. And that's how you cook your food with the propane. Now, the question is, how many grams of propane, C3H8, are needed to make 24.6 grams of CO2? So we're trying to get grams of C3H8 propane. We're given grams of CO2. You're also given the balanced chemical equation, plus 10 points each. 10 points each. And therefore, as soon as you say grams to grams in a balanced chemical equation, you know from important information that's a mass calculation for reactions. And the first step is whatever you're given in grams, you convert to moles. Second step is what you just converted to moles, you can of A, whatever you're given, you convert to moles of what you're trying to get to, your answer B. But your answer B is in grams, so convert to moles of B to grams of B. So you need 3 steps. This will be given to you. So if we look at number 4, First step, we're given grams of CO2. We convert it to moles of CO2. I have grams here. I want to get to moles. Use my good buddy, my good friend, unit analysis. Moles of CO2 go on top. Grams go underneath. Where do I get this ratio? 1 mole of a compound equals the molecular weight of CO2. What's the molecular weight of CO2? 1 carbon, 1 oxygen. That would be 2 times 16, 1 times 12, and add it up, and you get 44.0. And grams of CO2 divided by grams of CO2 cancel out. I get moles of CO2. Now, once you get moles of CO2, step 2 is moles of whatever you just figured to moles of the answer. And in this case, that's C3H10. But we're going to do step 2, moles of CO2 to moles of propane. Here's the moles of CO2 we just calculated. And we want to get the moles of C3H8 propane. This goes on top. This goes underneath. So where do we get the ratio of moles of propane? C3H8 to moles of carbon dioxide, CO2. One from the balanced chemical equation. When there's no number, it's 1. And 1 mole of C3H8 makes how many grams of CO2? How many moles of CO2? 3. And therefore, 1 mole of propane makes 3 moles of CO2, carbon dioxide. These are exact numbers, 3 significant figures. My answer has 3 significant figures. Am I done? No. But I see a question. I will do one more after the break. So the answer is yes, Disha, and for everybody else too. And now, what do I want to get to? Grams of C3H8, but I'm at moles of C3H8. So step 3, moles of B to grams of B, where B is what your answer should be in terms of the compound or element you're trying to get to. And how do you go from moles of C3H8 to grams of C3H8? Use your good buddy, your good friend, unit analysis. This goes on top, grams of C3H8. Moles go underneath. Where do I get these numbers? 1 mole of a compound equals Avogadro's number, which is I got thrown off track. 1 mole of a compound, hold a second, I got to reboot. 1 mole of a compound equals the molecular weight of that compound. The molecular weight of C3H8 propane, 3 carbons, 8 hydrogens. Each carbon has an atomic weight of 12.0. Each hydrogen has 1.01. Do the math. Remember, when you add, you have the same number of significant figures past the decimal to the right of it as the number that has the fewest. And notice this is 1, this is 2, 44.80 rounds off to 44.1. Put that in there. Moles of propane divided by moles. Propane cancel out. 3 significant figure, 3, 1 is the exact number, 1 mole. And my answer is 8.20. Now notice I have also here 8.22. Now I'm a round off at each step person, but if you just want to wait until the very end, you can, and I calculated both ways. Now, I think instead of going 5 more minutes and rushing, this is a good time to take a 5-minute break, and by popular demand, I will come back and do another one of those. So I'll see you in 5 minutes at 9:40. 951. Let's call it 951. I went a minute over. C in 5.
Can I ask one question real quick?
But
To get grams, we always have to find a molecular weight.
for a compound, yes. Remember,
Okay.
the sum, the molecular weight of a compound in grams is the sum of all atomic weights.
Okay. Thank you.
You're welcome. I'm going to take my break. Let's get going. All right. Again, for these type of questions where you have given a balanced chemical equation and asked to go from grams to grams, that's mass or weight, you convert the weight or mass of whatever you're given to moles of that. You convert the moles of whatever you just calculated to moles of your answer, B. Then you convert the moles of B to the grams or mass of B. And let's do one more. All right, thumbs up, people. Do you see number 5 on your screen? Thank you. All right, for the following reaction, hydrogen gas H2 reacts with chlorine gas to give 2 molecules of HCl, which I'll teach you later in the semester, is hydrochloric acid. But before I do this, I just remembered a quick announcement from Dr. White. This morning, This morning, I uploaded your lab scores for labs 3, 4, and 5. If you haven't handed in your labs, you're going to lose a lot of points. I'll probably put out an email, probably tomorrow. Today, I'm really booked up with a lot of stuff to do, but I'll put out an email that I'm going to do an amnesty program one time this semester. If you're missing any labs, get them in by next Sunday, say 8 p.m. or 9 p.m. Sunday, and I won't take off any penalty points and I won't give you a 0 because they haven't turned in a lab. Labs are 10 points. You don't hand in a number of labs, you're losing a lot of points. Like 3 labs you haven't handed in, that's 30 points. That could be the difference between an A and a B or an A and a C, or worse. So hand in labs. Now, most of you are, thank you. So let's get back to the problem at hand. Hold on, my glasses are dirty. Now they're clean. All right. You're trying to find how many grams of chlorine are needed to make 125.6 grams of hydrochloric acid. And we have, what are we trying to find? Grams of Cl2, chlorine. What are we given? Grams of HCl. Oh, well, in that case, thank you for letting me know, whoever did. Once in a while, I make a mistake. So time out while I correct something. You're right. All right, thumbs up, people. You see upload assignment, no, lab 7 on your screen now? You see I've changed the date. Due date is tomorrow by 4 p.m. So thank you for letting me know. That happens once in a while. I picked the wrong date. I'm off by one day. If that is through the powers granted me by the sheriff of DuPage County, no, I don't even know the sheriff. I'm sure that person is a fine person, but I can change due dates, and I just did. And let's go back to our problem. Since I've been jumping around on Blackboard, everybody see problem number 5? Thumbs up, people, on your screen. Thank you. All right, we're trying to find how many grams of chlorine when you're are needed to make 125.6 grams of HCl, hydrochloric acid. Notice I'm going from grams to grams, and you have a balanced chemical equation. When that happens, you need to do 3 steps. Step 1, whatever you're given in grams, you convert to moles. So I'm given grams of HCl, I'll convert it to moles of HCl. How do I do that? Use unit analysis. Your good buddy, your good friend, unit analysis. Love that whistle. All right, I have this number. That's the only thing I have to work with in terms of numbers, 125.6 grams of HCl. And I'm trying to get the moles of HCl. Multiply this times the ratio. Moles of HCl go on top, grams go underneath. Where do I get a relationship between moles of a compound, HCl, and grams of a compound, HCl? 1 mole of a compound, this is from important information, test number 2, 1 mole of a compound equals the molecular weight of that compound in grams. So what's the molecular weight of a compound? Oh, look, it even says that in important information. The molecular weight of a compound is the sum of all atomic weights in that compound. So to get the molecular weight of hydrochloric acid, HCl, I have 1 hydrogen, 1 chlorine to 3 significant figures. Remember on test 2, it will say, please use all atomic weights to 3 significant figures. Hydrogen is 1.01. Do not put down 1.008 because that's going to lead you to incorrect answer. When I see that, I'll take off a point because you didn't follow instructions. Chlorine to 3 significant figures, 35.5. Don't put down 35.45. Round it off before you add. Add it up. 2 significant figures past the decimal. 1, round this off to 1 past the decimal. The molecular weight of HCl is 36.5. 1 mole of compound, molecular weight, grams of HCl divided by grams of HCl cancel out. I'm left, notice 4 significant, 1 is exact number, 36.5 is 3 significant figures. So my answer is, I'm going to round off. I'm going to round off at each step. This is one of those you can do at the end or each step. I'm an each step person, and I rounded it off. Now, step 2. Whatever you've just found in moles, in this case HCl, we convert that to moles of our answer, and that's chlorine. So I want to go from moles of chlorine, step 2. It even says it on the, oh, that was a lame joke. Oh, look out, it's lame joke Monday. All right. Moles of HCl I want to convert to moles of my answer, which I'm trying to get to grams of chlorine, Cl2. So I'll, at this point, use moles of CO2. This is what I have to start with, moles of HCl. Trying to get the moles of chlorine. That's the units of my answer. Whatever I'm trying to get to goes on top of the ratio, moles of CO2. Whatever I don't want, my answer unit-wise goes underneath the ratio, moles of HCl. Where do I get a relationship between moles of chlorine and moles of HCl, hydrochloric acid? The balanced chemical equation. When there's no number, the coefficient is 1. 1 mole of chlorine reacts to make 2 moles of hydrochloric acid. And therefore, 1 mole of chlorine makes 2 moles of HCl. These are exact numbers. Moles of HCl divided by moles of HCl cancel out. I'm left with moles of chlorine. 3 significant figures, exact number. So I get 1.72 moles of chlorine. Now, am I done? No, I need to get grams of chlorine. How do I do that? I now do step 3. Whenever I just determine moles of B, which is the structure of my answer or formula, I convert to grams or mass of B. And this again is an important information, test number 2. In the past, students had to memorize this. No longer. Thank you, Dr. White. You're welcome. And now step 3, moles of chlorine, B, to grams of chlorine, B, what we're trying to find. And I have moles of chlorine that I just calculated in step 2. I want to go to grams of chlorine, and whatever I'm trying to get to goes on top, grams of chlorine. Whatever I'm trying to get rid of goes underneath, moles of chlorine. And where do I get a relationship between moles of a compound and grams of a compound? 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. So first I have to get the atomic weight of HCl, then I can use this in my ratio. So over in this corner, not HCl, chlorine, I'm sorry, Cl2. What's the molecular weight of Cl2, chlorine gas? There are 2 chlorines. Each one has an atomic weight of 35.5. 2 is an exact number. Multiply it, you get 71.0, which is 3 significant figures. 1 mole chlorine, 71.0 grams of chlorine. Moles of chlorine divided by moles of chlorine equals the number 1, which means to cancel out. I'm left with grams of chlorine. 3, 3, 1 is an exact number. The weight would be 122 grams. And if you notice, I have there both ways. And what that means is if you do like I do, round off at each step, that's what you get. If you do what you'd like to do and other chemists do, round off at the end, you get the same thing. And the rest are similar examples. Any questions about what I just covered? Yes, it will be on test 2 coming up this Thursday. So make sure you got plenty of time, got all today, tomorrow, and Wednesday. So a nice guy. And we should have worked on it over the weekend. I hope you did. And I've structured the course so I don't end a day or 2 before a test. I give you plenty of time to practice. Remember, practice will help you get a good grade. And I think it'll put a big smile on your teeth when you get a good grade. All right. In that case, I'm going to move on to new stuff that will not be on test 2, but will be on test 3, which is next Thursday. It's July, and we're going to be doing a lot of testing on Thursday. That's summer. All right. Last week we finished up talking about pressure. And just to remind you, pressure is force per unit area, but you should know .760 torr equals 760 millimeters of mercury equals 1 atmosphere. And that will be given to you in important information test 3. And I see a question. Rain, the answer is 4 tests and 1 final. And Disha, thank you for helping out. You were correct. Just in case, hold on. Time for a important commercial from Dr. White. Everybody see Blackboard on your screen announcements? Oh, hold on. Now you should see it. Everybody see it on your screen now? Thumbs up, people. Dr. White to class, Dr. White to class. Do you see announcements on your screen right now? Thank you. Some of you, I got to get to the quicker thumbs up people. All right, now, just so you remember, see where it says syllabus? Click on that. And oh, look, student course syllabus. And I have both PDF and Word document. I'll open up the Word document. And I opened it up, and this is same as the PDF. If we scroll down past stuff I'm reading all, notice I have, there will be 4 one-hour tests. This is under page 9. Here are the dates. And there'll be a final exam on this date. And if you also scroll down, you can see in the tentative course schedule, the week of this week, 7/12, test number 2 on Thursday. Next week will be test 3. And then on Monday will be test number 4. And then the final the following Monday. I've moved it slightly because we started on a Tuesday, remember, not a Monday. And we're going to end on a Monday so I can do this. Otherwise, it'd be, so we got plenty of time. And notice essentially the last week will be review for the final exam. I'll spend a couple of days doing review. I do that in fall and spring too. So always look at the syllabus. That's your place to go. If you have questions, you can ask me too. And all questions are good questions. Thank you. They're 4 tests. All right, so we went through conversions last week. I'm not going to do this again. And now we're going to move into another area of gases. All right, can I have everybody's attention? Did that get your attention? Everybody take a deep breath. Let it out. Take a deep breath. Let it out. Take a deep breath. Let it out. Now stay relaxed. We're going to be doing some stay relaxed. Algebra, stay relaxed. I'm going to show you how to do it in case you weren't good at it in high school or wherever, or you forgot how to do it. I teach everything you need to know for a test because in my class, I don't assume you're going to know anything except one thing I assume you know your own name that I won't teach you. But anyways, we're going to do some math and just relax. Now, the next two things I'm going to teach you about are two important types of formulas, mathematical formulas, deal with what's called the gas laws. A gas law is something that's always true. Any law is always true. If it's not always true, it can't be a law. So by definition, if I say the gas laws, these are mathematical relationships between measurements of different things you can do with a gas that are always true. Now, where did they come about? Well, if you go back in our history, back about the 1700s, what was happening in the world? The Industrial Revolution. And what made that possible? People discovered forms of energy besides just using your muscles. And what forms? First, there was the water wheel, but soon afterward came the steam engine, which was a great advancement, mainly in England that came first. And then after that, the combustion engine, otherwise known as the gas engine, like the one in your car. But that also could be used to move things and power equipment in factories to make things much quicker, more of, and at a lower price. Things like in England were known for textiles. If you know your American history, when we were an English colony, and even afterward, we shipped a lot of raw cotton to England where they made into fabric, which made clothing. And they were a powerhouse in that. How did they do that? Industrial revolution, machines, and machines powered by combustion engine, later our first steam engine and combustion engine. And what do they both have in common? You have a piston and a cylinder that goes up and down and compresses and expands because of gases and the structure of the machinery. So Boyle was an English chemist who discovered an important relationship. Now, something is my own personal opinion, but I think it's pretty valid. Most of the big advances, a lot of them in chemistry, I think in a lot of science, has been because of money. If you could find a way to help make better engines or things that would help you do that, like a steam engine, you can make money. And that was something that empowered chemists and scientists to do things. And still today, the same thing. So let's look at Boyle's law. And Boyle's law is, now this part, I'm going to read it, but don't ever read it again. The volume of a sample of gas is inversely proportional to the pressure applied to the gas if the temperature is kept constant. So at constant temperature, Boyle's law is P1 times V1 equals P2 times V2. And P and V can be in any units. That's not always true for gas laws. So what does this mean? Well, let's go to the whiteboard and find out. Boyle's law, P1 times V1 equals P2 times V2. Good news, this will be given to you in important information. Test number 3. What is P1? P1 is the initial pressure. V1 is the initial volume. And P2 is the final pressure. And V2 is the final volume. And generally you're given P1, V1, and one of these two you're given, the other you're asked to calculate. And that's how you use Boyle's law. Again, this and all of this you'll be given in, hold on, I'm gonna do something quick. All right, everybody see now Boyle's law, P1 times V1, P2 times V2. I have P1 initial pressure, V1 initial volume, P2 final pressure, V2 final volume. That's from important information test number 3, which you're not doing this Thursday, but it will come up soon. And in the past, students had to memorize this. You don't. So if we look at this, how do we use it? Well, let's find out. Hang in there, I'm writing this out. In real life, you'd be watching me do this on a whiteboard. All right, thumbs up, people. Can you see the problem? 8 points. A balloon has a pressure of, thumbs up, people. Hold on, let me check. All right, is today slow? Thumbs up. All right, I'm going to have to find the right thumbs up, people. All right, let me decode this in case you can't read my printing. A balloon has a pressure of 751 torr, that's pressure units, and a volume of 7.51 L. L is for liters, volume. What happens to the volume of the balloon if the pressure is changed to 401 torr? So what are we being asked to do? We're asked to find what is the volume. Well, that's really the final volume that we're trying to find, the final volume. What are we given? If you look up here, the initial pressure, the pressure initially, P1 equals 751 torr. The volume, V1, the initial volume, is 7.51 liters. And what are we also given? If the pressure is changed, that makes it the final pressure, P2, to 401 torr. As soon as you see volume and pressure, I know Boyle's law, P1 times V1 equals P2 times V2. What are P1, V1, P2, and V2? Good question. And if you look at important information, P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, V2 is the final volume. And that's what Boyle's law is, like as you see right there. All right, watch closely, because now we're going to do some algebra. What are we trying to solve for? V2. I want it alone on one side. When you have multiplication or division, for this class, multiplication, if I want V2 alone on one side, I've got to get rid of P2. How do you get rid of something like that in a multiplication? Anything divided by itself equals the number 1. So to get rid of P2, because I want V2 alone on one side, because that's what I'm trying to solve for, I'll divide by P2 because of this. But whatever you do to one side, you have to do to the other. Well, I did that. If I divide this side by P2, I have to divide that side by P2. P2 divided by P2 cancel out, becomes the number 1. So this is now V2 equals P1 times V1 over P2. Why did I do this? Because I wanted V2 alone on one side. Now, you don't have to do this, but it's a habit of mine. So good habits, Dr. White doesn't change. I'm going to rewrite this like this. And now, since I took the time up here to look at what's P1, what's V1, what's P2, I can plug it in. And I will. P1, 751 torr. V1, 7.51 liters. And P2 is 401 torr. Now, before I pick up my calculator, I look at this and say, oh, look, I have torr divided by torr. Anything divided by itself cancels out because it's number 1. So this cancels out. I'm left with liters, which is a unit of volume. So I know I set it up right. And now, since the multiplication division, I know I will use 3 significant. Oh, Dr. Whiteson is 3 significant figure run. And now I'll pick up my calculator, which I'm doing right now. And my calculator gives me this number. I always laugh when a calculator gives. And if I round this off, I want three significant figures. Keep the 1, keep the 4, keep the 0. Use the 6 to round off. That'd be 1 point. That's 5 or greater. Drop all this, increase this by 1. 1.41 times 10 to the first liters. So that was what would happen, and it would increase. And that's Boyle's law. And Boyle's law deals with gases, especially not only balloons, but mainly cylinders. Well, let's go through this again. First of all, I have some tea. We have figured out what are we trying to find. If the pressure is, what is the volume? What happens to the volume? That's the final volume, V2. We're given initial pressure, initial volume. All right, Rain, come to my office hour this evening if you can, and I'll help you out. Or tomorrow morning before class or after lab. Thank you. That's why I have my office hours. And good news, time for a commercial from me, the host. When I teach during fall and spring, because I teach at 2 schools, right after class, I've got to run away to go teach at the other school on Monday and Wednesdays. And usually I try and get early, but I really don't have office hours. And COD doesn't ask part-time faculty, adjuncts, which most of the college is, to have office hours. However, with the Zoom, I don't have to drive to COD or my next class, or if I had an office hour when I'm not teaching, like tonight, I don't have to drive special trip to COD, and neither do you. So remember, I have office hours on Monday and Wednesday. This Wednesday will be 8 p.m., but the rest of the semester, and I'm there to help you. All right, so we figured out we're trying to find V2. We're given initial pressure, initial volume, and a final pressure. If the pressure is changed to something, that's the final pressure. When you see a gas and pressure and volume, you know Boyle's law, P1 equal V1, P1 times V1 equal P2 times V2. We want to solve for V2 to get rid of the P2, we divide it. Whatever you do to one side, you have to do the other, so I divide that also by P2. Anything divided by itself becomes the number 1, it's cancel out. So I have V2 on this side is still P1 times V1 divided by P2. I rewrite it, you don't have to, I like to. Put my numbers in that I took the time to figure out. And here's my answer, 3, 3, 3 significant figures. Oh, that was fun. Let's do another one. All right, a cylinder. Oh, by the way, your instructor, me, Dr. White, never had any inklings of ever going to art school. My mother was a very good amateur artist. She loved to paint. None of that rubbed off on me. My father was real good at wood carving. Nope, no artistic with molecules and atoms I do, but not with wood or paint. But anyways, I should warn you, now and later in the semester, I'm going to do some artwork. It's totally acceptable to laugh yourself as hard as you want, because I'm not a good artist. But anyways, let's look at a cylinder. And just like in your car, a cylinder has a plunger inside of a cylinder, and you can move it up or down. And that plays an important role of the gas that's right here. So what do we have going here? We have a cylinder has initial pressure. Well, first of all, what are we being asked to find? I'm going to let you try that first. Read that problem. A cylinder has a pressure of 759 torr and a volume of 18.6 liters. What happens to the pressure if the volume is changed to 0.511 liters? First of all, what are we being asked to find? Time's up. The final pressure, which we do P2, or some people do PF. I'm a number person. So what are we given? I'll let you take some time right now to figure out hint P1, V1, P2, V2. By the way, click, this is on the test, big time. When I do something like this, I hope by now you know that I'm doing that for a reason. All right, give you about another 22.5 seconds. Go. We're into bonus time. Time's up. All right, what are we given? We're given the initial pressure, P1 equals 759 torr. It's good to put the units when you're figuring out what are you given. And a volume, initial volume of 18.6 liters. And a final pressure, or what we're trying to find the final pressure, P2, and we're given a final volume. If the volume is changed to V2, 0.511 liters. And as soon as I see that, I say to myself, well, I've only got pressure and volume, and I'm dealing with a gas, so that means Boyle's law. P1 times V1 equals P2 times V2. And remember Boyle's law, which will be given to you, important information, test number 3, which is not this week, but it's coming up. P1 is initial pressure, V1 is initial volume. P2 is final pressure, V2 is final volume. And now, what do I have to solve for? And the answer is P2. With letters here, the variables, you try and solve for P2 on your own. Don't put the numbers in, just the variables. Go. Remember, you want P2 alone on one side. All right, I'll give you another 17.8 seconds. How do you solve for P2? Just the letters, not numbers. That's about time's up. So if we look here, we're trying to find P2. That means we want it alone on one side. Uh-oh, look what's in the way. V2. How do we get rid of something when it's multiplied times another number? Anything divided by itself equals the number 1. Cancels out. So if I want to get rid of V2, I'll divide this side by V2. Whatever you do to one side, you have to do to the other side. And therefore, I'll divide that by V2. And now, notice this cancels out. I'm left with P2 equals P1 times V1 times V2. And I'm going to rewrite this P2 equals P1 times V1 over V2. What's P1? Well, we took the time to figure out 759 torr. What's V1? 18.6 liters, because we took the time to figure that out. And what's V2? 0.511 liters. Now, before I do anything, I'm going to look at my units. I have, if we look at this down here, I have torr times liters divided by liters. And notice anything divided by itself cancels out. And the only thing I'm left with is torr, which is pressure. So I'm on the good, doing a good thing. And now let me turn on my calculator, clear it. And the number my calculator shows me is this. I'll let you round that off to how many significant? Oh, he's in his rut. 3, 3, 3. So round this off to 3 significant figures. Time's up. Keep the 2, keep the 6, keep the 8, or keep the 8. Getting ahead of myself, which happens. Keep the 8, use the 8 to round off. Is that 4 or less, 5 or higher? 5 or higher, increase that by 1. And the answer is 2.68. Increase it by 169. 2.69 times 10 to the fourth torr. And I see someone has a question, and let me check. All right. Let me redo my calculations, see if I made a mistake, which happens. I see where I made a mistake. I put an 18.1, or it should be 18.6. Now, if you do that on a test, but show your work, and I say, oh, you got a math error, I only take off 1 point. If it was multiple choice, you would have lost everything, which is why I don't do multiple choice other than a few some tests. All right, let me get back to work. And the answer is, you're right, I was wrong. Thank you for correcting me. Let's go back here. If you go back and look at the first video, first class, I do admit I make mistakes sometimes. Round this off to 3 significant figures. Keep 2, keep the 7, keeps the 6. Use 2 to round off, it's 4 or less. So the answer is correctly now this. So when you reduce the pressure, I'm going to go another 2 minutes or 3, another couple minutes, then we'll take a break a little longer later than I would have liked to, but I want to finish this, and there's an important thing I want to teach you. We start out at 559 torr, or which would be by lowering the volume, we've increased the pressure dramatically, almost 1,000 times higher, approximately. And what happened? Initially, you had here P1. Now the plunger is going to go down to a lower volume, because right now we're at V1. Right now we're at V2, and the pressure P2 has gone way up. What happened? You've compressed the gas. By pushing it together, the pressure has gone way up. How many of you have ever filled a football, volleyball, or soccer ball, or your bicycle tires with a hand pump? Any of you? Let's check this out. I'm going to a different view right now. Thumbs up, people. Have you ever pumped up a bicycle tire vac or something else? You use a hand pump. How does that work? By pushing the plunger in, the gas inside the cylinder is compressed. and the pressure, as you just saw from Boyle's law, goes way up. Now, how many of you ever seen or even used in a gas station to fill your car tires with air? What do you use? A compressor. How many of you have ever done that? Thumbs up. I see some people say yes and that. Boy, a lot of you have never done your tires. I check them once a month. And what is a compressor? It's the same thing except with a motor causing the plunger to go down and compress the air. When it comes back, brings more. Usually they have what's called a ballast, a tank, where it can store that high pressure gas, which you then put into your tire. Bet you didn't think about it. Your car tire has gas in it that's compressed at a higher pressure. That's why it's inflated. And with that, I better let you take a break. I'll come back in 5 minutes, come back at 10:55, and we'll continue on with gases. Let's get going. All right, so Boyle's law teaches us that if you compress a gas, the pressure goes up. So next time you're going by a gas station or in a gas station with a friend or a neighbor or loved one, you can tell them, you know, that compressor over there works by Boyle's law. P1 times V1 equals P2 times V2. People don't want to hear chemistry in a gas station or near a gas station, but now you know. Now, next week, we'll go through some more problems with Boyle's law when we do the practice problem. So let's continue on. All right, thumbs up, people. I've got the wrong thing up, so I'm not going to tell you to check. All right, that's Boyle's law. We did our practice time. All right, everybody, click the switch. Will this be on test? Charles' law is in the off position. And let's just quickly look at Charles' law. And another English chemist, this is another gas law. And again, switches off, click. It is the volume of a sample of a gas is directly proportional to its Kelvin temperature if the pressure is kept constant. When we deal with gas laws, instead of using Celsius, it's always in Kelvin. But you measure it in Celsius to convert to Kelvin. But Charles' law, which is V1 over T1, equals V2 over T2. V1 is initial volume, T1 is initial temperature, V2 is the final volume, T2 is the final temperature. Now, whenever I put this on a test, students have trouble solving for V2 or T2 in a fraction like this. So I finally decided a couple of years ago, I'll show you it and talk about it, but I won't have it in a test question or on the final. That's Charles' law. And remember, temperature is always in Kelvin. To go from Celsius to Kelvin, Kelvin equals degrees C plus 273. Oh, look, I wasn't lying to you. You notice Charles' law will not be on any test or the final exam. It's on your screen, on your monitor, so it must be true. But it is. Now, next couple of slides, part of them, I'm going to go click. It's good background information, but I'm going to be teaching about boiling. Have you ever boiled water at home? I hope you have, even though when I was in grad school, my neighbors right across the hall in the apartment building I lived in, which was all students or grad students, it was 4 girls, and one of them was from one of the countries in Latin America. I think it was Brazil. And she was from an extremely wealthy family. She had never boiled water on her own. She always had servants. And one time they almost had a fire. Luckily, I happened to be walking by and their door was open and I helped them out. She decided, oh, I'll make buttered toast. And she put the butter on the bread and put it in the toaster. No, you don't do that, because she had never done that anymore. But I'm going to assume all of you, at least at one time, either boiled water or watched someone else boiled water. We're going to talk about boiling. But the next couple of slides, I'm going to give you some definitions that won't be on test. All right, when we talk about boiling and vapor pressure, the pressure of vapor, which is really a gas, I'm going to talk about things that are not in the text for those of you reading the textbook. All right, when we talk about liquids, liquids can evaporate. And evaporation, again, switches off on this slide, in which molecules escape from the liquid phase to become gas. And therefore, if we have water evaporating, like when you dry something out in the air, the water goes from a liquid to a gas. and we call that evaporation. Now, the rate of evaporation is based on the temperature. Evaporation happens quicker rate for hotter liquids than cooler ones. So the hotter you have something, the more evaporation can happen. And one of the nice things or interesting things about evaporation is when you evaporate something, when the liquid comes off something like your skin, this takes energy to evaporate it and it makes it cooler. Now, I don't know if you call this sexist or not, but men sweat, women perspire. And if you've ever played tennis when it's super humid out, for me, I'm dripping all over the place. I don't even bother with a headband because that's soaked within a minute or two when it's super humid and warm out. I have a couple of towels on every point or something. It's been a while since I played tennis because unfortunately my tennis buddy a couple of years ago got transferred out of the area, so he's no longer there here to play tennis with. But you'd be dripping. Why are you perspiring or sweating? Because when you have that liquid on your skin and it evaporates, it cools down your body. Another example of that everybody see on your screen, the blue on the right, it's called cooling towers. And you see a big fan on top. You see pipes coming in. And what happens is you've got pipes in here and you're cascading water over those pipes that carry also water. And the water that's cascading, because of the cooling tower, fans are pulling water straight up through vents here, right, like right here. That's causing the water on the outside of the pipes to evaporate and causing the water inside the pipes to get cold. And that's how you have cooling towers. At one company, my knowledge of cooling towers luckily saved my life and a lot of other people because something was heating up to the point it was about to explode. We had the water full on. And I knew, see these fans here? They're huge. You're talking about at least 6 to 10-foot diameter. And the motors to drive those are huge, meaning take a lot of electricity. Well, at this one plant, I knew the plant manager was always trying to save money. And he could get away with just running one fan for most of the stuff. Well, when the temperature was going up and the people in the control room looked at me like, should we run away? And immediately I thought, I knew the plant manager and I asked the person by the controls for those fans, how many fans are on? He said one. I said, turn the other 3 on now. And he did. And we all got religion quickly. And that was enough to add additional cooling to the water to stop from the reaction blowing up. It was 40,000 pounds. And if it blew up, I wouldn't be here today. Surprise, it didn't. Thank you, Rain. It is. That's part of my experience of working in chemical plants, knowing these things, because you never know when information can help stop a problem from happening. All right, so we have evaporation, which water becomes, usually water, it can be any kind of liquid, becomes a gas. And that's how you get cooled when you perspire. When it's super humid, the humidity is already in the air, so it takes a lot longer for it to evaporate, and that's why it doesn't cool you as well. All right, now, again, switches off. We talk about a vapor, that's a gaseous molecules. Molecules is a gas. of a substance at a temperature and pressure at which ordinarily it would be thought to be a liquid or solid. So normally water at this temperature, like 72 or whatever, will be a liquid, but if it evaporates, you call that gas a vapor. Now, vapor is a gas, so you can measure the pressure. And there's a concept called equilibrium. That's the condition, again, switches off, which two opposite processes take place at the same time. And like I said, vapor is a gas, so you can measure the pressure of that vapor like above a liquid that's giving off the vapor like water, like a pot of water. And a volatile substance, again, switches off is something that evaporates very quickly at room temperature because it has a high vapor pressure. There's a lot of gas being formed. Gasoline is an example of that, and do not check this at home ever. Now, what is boiling? Boiling is a special form of evaporation where conversion from liquid state to vapor state occurs within the body of the liquid through bubble formation. When you boil water, those bubbles you see in the water are water vapor, water molecules as a gas. And that's why they form those bubbles and they float up because they have a lower density than the liquid. All right, warning, warning. Dr. White, artwork time. And by the way, if you crack a rib laughing, you can't sue me. Here's a beaker of water. Let's put it on a hot plate. There's this control. It's plug, it's grounded that you put into a wall socket. And turn it on. And after a while, you'll start seeing some bubbles here. And these bubbles will rise to the surface and collapse. And what's in them? Water as a vapor. And the gas is coming this way. As a gas, it has a pressure, which we call vapor pressure. Now, the boiling point switches on. I won't ask the definition, but you should understand it. The boiling point of a liquid, that's the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure exerted on the liquid. So at boiling point of a liquid, the temperature where it boils, the vapor pressure equals the atmospheric pressure. So when the atmospheric pressure equals the vapor pressure of water, and you measure that with a thermometer, that's the boiling point of water. Well, what's important? What is the atmospheric pressure? That changes. And the switch is on. On our planet Earth, which we all discussed the first day, none of us are going to be leaving during this semester, at least I hope not. And when you go to higher altitudes, the atmospheric pressure drops. When you go to higher altitudes, the atmospheric pressure drops. Here in Chicago, we're at sea level, 1 atmosphere, 760 torr. If you go to Denver, the Mile High city, is a lot higher, and atmospheric pressure in Denver is always much lower than in Chicago. If you ever have any friends that live in Denver, you know that they know, and it says on the package of stuff they buy, to cook something, you have to boil it longer. Why? Because the atmospheric pressure is less. Hint, you should know this. And because the atmospheric pressure is less, the boiling point temperature is lower, and that's why it takes longer to cook it. Now, what would happen to the boiling point of water if you go to the top of somewhere Dr. White will never go to? I don't like heights. If you go to the top of, and I'm not a mountain climber, but what if you go to the top of the Himalayan mountains, the tallest mountain range on our planet? When you go much higher, the atmospheric pressure is down. Therefore, you need less heat energy to make water boil to get the vapor pressure equal. And therefore, the boiling point on top, if you go to Kathmandu, which I've never gone to and I don't plan to, not that I wouldn't like to, but anyways, that's the starting point for climbers who go to climb the Himalayas, which is quite high altitude. Guess what? The boiling point of water is much lower. Hold on, let me see something if I can find it. Don't you just love Google? I do. Well, Nepal is high enough near Mount Everest, near the top, that in Chicago, the boiling point of water is approximately 100, depending on the weather. It's a little lower or higher. But in Kathmandu, or in Nepal, which is near Kathmandu or in the area, it's 70 degrees C, 30 degrees lower. Wow, let's see if this one gives us the right answer. Nope, that's not what I was looking for. Here's one of those, which is, it's about 70 in Kathmandu. You should know what happens to the boiling point when you go higher altitude. It decreases. Why? Because the atmospheric pressure is less, you need less energy, less heat, therefore the boiling point is less. The higher up you go altitude, the lower the boiling point of something. And if you read science fiction, one way to kill someone in outer space is throw them outside your spaceship without a spacesuit on. Why? Because the atmospheric pressure in space is almost zero, and that causes your blood to boil, which means it will explode in your body and you're dead. I'm sorry to bring that up. And if you've ever seen Arnold Schwarzenegger's really good movie called Total Recall, on Mars, when they get out into the surface, somebody dies that way. Not a pleasant way. I think this is really a pleasant way. No, I don't want to get into that. But anyways, you should know that. Now, what's the opposite? A pressure cooker. And a pressure cooker cooks food quicker. Why? Because you put some water in there, heat it up, but it's sealed. So the pressure in a pressure cooker gets a lot higher than atmospheric. Because it's a lot higher, that means the water that's in the pot that you have the pressure cooker is a lot higher temperature, and that causes the food to cook quicker. And that's how a pressure cooker works. Thank you. All right. So you should know, let me write this down on a whiteboard. I'm not sure if I'm spelling this right, altitudes. But anyways, at higher altitudes, the atmospheric pressure drops and the boiling point of a liquid decreases because you need less energy to have the vapor pressure equal the atmospheric pressure, which is why if you ever take a plane, the cabins are pressurized, one, so you have enough air to breathe. At higher altitudes, there's less air, lower pressure, it's harder to breathe. That's why if you ever watch some of the shows on people who go up these super tall mountains like Mount Everest, which will never be mine, they start at a base camp, stay there for a while, and get acclimated to the lower pressure. Or sometimes they'll breathe their own oxygen. Now, the people who live there in Nepal, very high altitudes, their body has been acclimated to that lower atmospheric pressure. So that's why they don't need masks or things like that. That's why they make good guides, like I believe the Sherpas. Why I'm going by memory now. All right, and that's now you know what controls water boiling, the temperature, and what are those little bubbles inside? Water vapor. Water is a gas. All right, let's move on. All right, and the normal boiling point, which I'll never ask on a test, is the boiling point of liquid at atmospheric, which is 760 millimeters mercury, 760 torr, 1 atmosphere. Chicagoland. Now, switches off, volume in moles. This is called Avogadro's law. He helped with gases establish that the volume of a gas is directly related to number of moles of a gas when the temperature and pressure are not changed. And switches off here, this can be derived by the ideal gas law. And at STP, STP stands for standard temperature and pressure, which is 270 Kelvin, 1 atmosphere. Avogadro found that 1 mole of a gas equals 22.4 liters. And this helped a lot in determining the whole concept of moles, which is why Avogadro's number was named after Avogadro, even though that number, he wasn't the one who discovered it. All right, let's talk about the ideal gas law. In all of chemistry, my favorite chemical or mathematical calculation is the ideal gas law, PV equal nRT. Switches on. If it was a dial that I could only turn to 10, I've just turned it to 20. That you should know this. And this is an equation that includes the quantity of gas, the temperature, pressure, and volume of a gas. P. Oh, by the way, see, even on the slide, I have this. In the past, students have to memorize this. You will be given everything in the important information, test number 3, but you still have to know how to use this. Now, PV equal nRT. P is pressure. is always in atmospheres. V is volume. It's always in liters. N is the number of moles. And T is temperature in Kelvin. Now, R here is the universal gas law constant. And for the work I do as a chemist, there are different values based on the units of R. For our class and of what I've ever done, we'll use R as 0.0821 atmospheres liters per mole K. That's the units. This is a calculated number. You measure it by doing experiments in a lab. Therefore, this version, I am using 3 significant figures. I can easily go out on the internet and find R, the universal gas law constant, to a higher amount. Let's see if Dr. White's lying to you. And here they have it in joules, which is another unit. Huh, Dr. White's having, I can't find it day. Aha, got it. I knew it's out there. If you look here, let's see if you got it on your screen. Right here, you see 0.082057461 liters atmospheres per, this -1 means divided by Kelvin and divided by moles. They don't use the E here, I still do. And the 3 significant figures, 0.80820, 821, I take it back. And that's what I use. And so this is 3 significant figures. Now, let's look at PV equal nRT in a practical way. You should know this. PV equal nRT teaches you a lot about your car tires. Yes, your car tires. How's that? Well, your car tires are gas inside rubber, and they're enclosed in there. Now, true story. Well, I never tell you false stories. So I don't know why I have to say true story. But a number of years ago, it was a real cold winter here in Chicagoland. At that point, I lived in an apartment in the other part of northwest suburbs, not far from where I am now. But in that apartment complex, you parked outside. Now I have my own home and I have a 2-car garage that's partially heated. Some of the heat comes out, and so it never gets super cold there. But parking outside, it was super cold. And so Friday, I got home from work. I was working at a chemical company. I figured, because my battery, when the temperature goes down and other things in your car, you should run it, not let it sit for a day or two. And it was the weekend. Next day was Saturday. And the temperature in the morning, Saturday morning, overnight, it got really below 0. I'm not talking the wind chill. And it was like about 8 or 10 below that Saturday morning. It's about 7:30. I figured I can get all bundled up, take my car for a 10-minute ride. So I go out to the parking lot and I have an SUV. I go there and I look at, I have 4 flat tires. They were really low, not flat to the ground, but you could tell they were low in temperature. And for about 1.5 seconds. Oh no, what do I do with 4 flat? And all of a sudden, chemist kicked in and said, wait a second, PV equal nRT. What does that mean? Well, I'm going to teach you. PV equal nRT. Thumbs up, people. Everybody see my whiteboard? Thank you. All right, now, in your tires, the volume stays constant. N is the amount of moles, which is the weight. And R is the universal gas law constant. It's a constant. Well, if overnight and the gas in the tires got real cold, the temperature goes down. And guess what? If the temperature goes down and volume, moles, and the constants stay the same, the pressure has to go down. So because it got real cold, temperature got real low, the pressure got real low. And that was the reason my tires looked flat. It wasn't me, everybody around. When I looked at the other car tires, I saw that too. So what did Dr. White do? I went over to the local gas station. This is a long time ago. That's when everybody had compressors, which I talked to you about earlier. And I got there, and I was one of the first out, and I got there and I got that a compressor. They were free back then too, long time ago. And I hooked it up to my tires, and I started filling each one of the 4 tires up. And actually I pressured them a little more than normal, about 35 PSI. I think I went to 36 or 37, maybe not. But anyways, and by the time I did it, and I'm pretty quick at doing those, it took me maybe about 3-4 minutes. I look up and look over and say, wow, there are 10 cars in line waiting for me to get done. I got in there first. And I didn't tell them, you know, your tires are low because PV equal nRT. So in the winter, when it gets brutal cold, keep an eye on your car tires because PV equal nRT, the ideal gas law says the pressure goes down because the temperature goes down. Now, back about, I think it was the summer of 95, I was working at a chemical company in Great America in Gurnee, and I was living in the Schaumburg area. And if you remember, we had a brutally hot summer. I think for almost 2 weeks, the daytime temperature was above 100 degrees. And that was before we had cooling centers throughout the area. I think about 600 people, so sad, died from heat-related medical issues in the Chicagoland area. And after that, they changed where they now have cooling centers if it gets real hot here. I know COD opens their buildings up for cooling centers, like the chemistry building in the building we're in has good air conditioning, thank goodness. And so anyways, during that time, I had to drive a long distance on the toll road, and going home, and even in the morning sometimes, you see cars and trucks, lots of them, pulled over with blowouts. Why are all these blowouts happening? And then chemists kicked in and said, PV equal nRT. So let's look at this. Let me just remind you. Temp decreases and therefore the pressure in your tires are. Now in the summer, what happens to the temperature? It goes ways up. Not this summer, thank God, like that summer. But if you're on the West Coast right now, you'd be suffering because like in Death Valley, I think they said the temperature reached close to 130 Fahrenheit. Whoa. But anyways, so PV equals nRT. This should have been a lower cap, not a capital. nRT. And in your tires, the volume, unless you get a flat, and then all bets are off, the moles, the amount, and the universal gas law constant stay the same. These don't change. So what happens in the summer? The temperature goes way up. And when that happens, your pressure in your tires goes way up. And that's what was causing the blowouts. The pressure was already high in some of those tires. When it gets hot like that, I lower my temperature, pressure in my tires. Instead of 35, I'll take it down to 32 or something like that, or a little lower, and keep an eye on it. And the pressure goes up. And for those cars who already had pressure at a certain level, when the heat from the outside and also when you drive, the friction of your tires on the road causes heat. The combination caused the pressure to go way high. And guess what? They blew out. Just like if you take a balloon and blow it too long, it pops. Well, that's what happened to their tires. And it was not a fun thing. So let's do something because it's Subtle Monday. So if we look at our tires, there's gas in them, and you should know what governs the fact that in the winter, the pressure of your tires get real low when it gets real cold. And that's PV equal nRT. That's when the temperature goes down, the pressure goes down, because V, N, and R, volume, moles, and universal gas law constant R stays the same. So in the winter, when the temperature goes down, you should keep an eye on your tires because they're going to go down the pressure. In the summer, what happens? Gets hot here in Chicagoland, and the temperature goes up. And again, in your tires, volume stays the same, moles, the amount stays the same, and the universal gas law constant stays the same. So if the temperature goes up, the only thing on this side that's going to change, because P times V is always equal to N times R times T, the only thing that can change is the pressure goes way up, and that's where you can get a blowout. So now you can tell your friends, neighbors, and loved ones when it gets super cold out in the winter, and if your car's outside, check out your car tire pressure. If it gets super warm in the summer and your car's outside, check your car tire pressure, because PV equal nRT teaches you what happens. Now, if I look at what time it is, I'm not going to start a PV equal nRT problem. I'll do that tomorrow. All right, heads up, couple of things. First of all, one, if you're having problems with anything I'm working on or you should be working on, come to my office hours. Today, it will be at 5 until 6. If I have to go a little later, I will. I don't have a plane or train or bus to catch. So, and plus the hockey season is over, and so is the soccer season for at least till August when Bundesliga starts again. But anyways, come for help. Don't forget, Wednesday, I'm going to put out an email that I will start my office hour on Wednesday only at 8 p.m. and I'll stay as late as possible if you need help, because test number 2 is this Thursday after our lab around 10ish or so. I will send out the email for that. Make sure I showed you the announcement on Blackboard. You do the practice problems, because test 2 will have chapter 4 and chapter 5, part 1 deals with chemical bonds. And also we've already done that problem set We'll deal with mole-related stuff. We've done 2 of them. And then tomorrow, I'll also go through balanced chemical equations. And with that, oh no, I'm going to let you out a whole minute early. Shh, don't tell anybody. I'm letting you out early. With that, I'm going to say, gang is on. Oh, don't forget to turn your labs that are due. And I'll put out an email sometime tomorrow about amnesty program, 1 time only. With that, thank you for coming to my lecture today. Gang gesund. Goodbye.